Hello everyone, we meet again to learn about computers, and this week what we're going to learn about would be memory, microprocessor, and representation of data, meaning to say that we'll go with the first part, which is how computers represent data. Now at the top here I've written the word simplicity. Why? Because simplicity has great makeup. No, I'm kidding. Because the computer, even if it is a device that is complex, that can do lots of complex tasks, like for example you can play 3D games, or you can create great graphics, or you can do complicated calculations, in reality it all boils down to simplicity, even the way the computer represents data. We'll have a look at this concept. It's called the binary number or binary digits. Now, binary is otherwise known as the base 2, right? Meaning to say that it only has two numbers. Now, you know that numbers begin with 0, right? And we also have the number 1. So these are the two numbers which is in base 2, 0 and 1. Now, why is this simple? This is simple because the computer can now represent these two things using just, well, another two things. For example, it can represent these two things by having light or not having light. When there is light, there is 1, for example. When there is no light, then there is 0. Fairly simple, right? Next, we think about other things. Let's say, for example, your hard disk drive. It is called a magnetic disk drive. Now, you think about magnets, you think about two things, north and south. So this is another way of representing things, either north or south, one or the other. Now, because we are very much used to the system called decimal, right? I'll write this here, right? Decimal. Or otherwise known as base 10, we might find that base 2 is a bit hard to understand. Base 10, hard to understand. Why? Because we are so used to this system. We are so used to having numbers from 0 up until 9. So you find this, you know what, this is a bit hard to understand. Why do you have everything like this instead of this? Of course, actually, this is only simple and easy for us because we have known this since we're young, right? Not to know that the computer have known this since they were young, but it's just that this is actually the simpler method of representing numbers, right? So meaning to say that if you want something, you can just use a combination of 1 and 0. You do not need to know 2, 3, 4 and all of these things. So the computer does not need to know that. So it does not need to represent all of these numbers by way of, let's say for example, the computer uses light to represent a number, right? Let's say this is dark and this is light. Imagine if the computer has to represent all numbers from 0 up until 9, right? So it has to play around with the levels of lighting. The higher the number, the more intense the lighting. Brighter, 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 brighter. Now, okay, we said that's simple enough to do. Can't you represent that? Okay, but for the computer that is hard to do. How do I come up with higher values or brighter colors or brighter light? Once I've come up with that, not only do I write on things, let's say for example you have a DVD RW, so you write on the DVD using some kind of system of lighting that has brighter light and brighter light to represent 0 up until 9, right? So this is dark and this is brightest, okay, brightest ever. Okay, now if you're using dark and brightest ever for 9, then you will have to figure out a way to represent 2, 3, 4 and etc. Right? Now, once you've figured out that way, so you want to write on the DVD RW. So you write on it using different colored lights or different brightness of lights. Now comes the question of how do you read from the DVD RW? Now this is a problem as well. So instead of having all of this complicatedness, the computer says, you know what? I don't want this complicatedness. I don't want a maybe. I just want a yes or no, one or the other. So that's how the computer came up with a simple binary system to represent pretty much everything. It represents letters, it represents numbers, and a host of different things. And this thing is called binary number or binary system or base 2. And there's only two numbers, 1 or 0. Okay. Now, one binary number is what we'll call a bit. A bit. And this is the smallest number ever in a computer system. A bit can be either 0 or 1. Okay. Now, of course, as we increase the space that we can put a number, let's say for example, in our system of decimal number, human system of decimal number, we have, say for example, in the tens, or 100, or 1000, and etc. And as we increase the space, we can increase our number and make it bigger and bigger and bigger. Same with the computer. As it increases the amount of space, the amount of combination it can achieve also increases. Right? Let's say for example, we have space for one number. So the amount of possibility would be 2, meaning it can be either a 0 or a 1. As we increase this space, let's say we put another space here, again we can put a 0 or a 1. Right? Now, we can actually also do it like this. We can put 1, 0 or 0, 0 or 0, 1 or 1, 1. Right? 0, 0, 0, 1, 1, 0, 1, 1. That means we have a maximum of 4 combinations when we have 2 spaces. And we also find out that as we increase the space, it will increase by the numbers of 2, by the powers of 2, sorry. Right? So as we increase another space, for 3 spaces, we actually have this kind of combination, which is 8. As we increase the space further, 4, now we have 2 to the power 4, which is 16, and so on and so forth. And this is the binary system or base 2 system. Right? Now, as we increase the space further, we get to 8 spaces, and 8 is 2 to the power of 8 is 256 combinations. Right? And 8 bits or 8 spaces is 1 byte. Right, so I'll write that down somewhere, and maybe I'll just erase this. Right, so 8 bits is equal to 1 byte. Okay. And we'll have a look at why so. Actually, there is no reason why 8 bits is 1 byte. This is done through trial and error, and through history, people have tried out, what if 7 bits is 1 byte? What if 10 bits is 1 byte? What if 16 bits is 1 byte? So they did their trial and error and figured out this is the best number for 1 byte. It's like, why is 12 a dozen? We have no reason for that. I have no idea why it's 12 a dozen. Basically it's based on history. Someone somewhere who's very smart and influential just said, you know what, 12 is a dozen, so everyone has to follow that, something like that. But with regards to this, it is a consensus between mathematicians, I guess, computer scientists and whatnot. So decided 8 bits is 1 byte, which makes a lot of sense because 256 combinations is enough to represent pretty much everything that we have on our keyboard. It can represent ABC until Z, capital ABC until Z, right? All the numbers you have on your keyboard, all the symbols like equal to signs or dash or comma, or all of these small numbers, asterisks, all of these symbols can be represented and encapsulated in 256. You do not need much more. So they figured, you know what, this is pretty nice, so let's just go with this. 8 bits is 1 byte. But now that we've talked about that, we can go on further to numerical systems, binary or base 2, and then we can talk as well about decimal or base 10, right? So now we'll go to decimal or base 10. Yeah, it's a bit dry here, so what happens is that the ink of the marker gets dry fairly easily, so you can see some kind of residue even as I erase it. Anyway, next is the changing of numbers, or rather a conversion of numbers from binary to decimal and vice versa. We'll have a look at the decimal numerical system. Let's say we have actually any kind of numerical system goes like this, right? The smallest number will be on the rightmost. Let's say I give you this number, 792. Okay, that's not very clear. Let's write that again. 792. Now here, although in the decimal system of 0 up until 9, right, so you know what, I'll write that one by one, right, and I'll write that using a blue marker. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know this is a bit funny, but hopefully you understand what I'm trying to say. Basically here, I'm putting 7, 8, 9 here because we have 7 and 9 here. 9 is a larger number compared to 7. But because of the positioning of 9, which is on the right side of 7, we know that 7 here is the bigger number because this is a 100. Right? This is a 90s, it's in the tens, and this is a single number, right? Single number. HTS, not HTC. 700 is larger than 90, right? That is common sense. So the same goes with any kind of numerical system. And we go one by one until we reach the maximum. Let's say, for example, I add 8. Let's say I add 1 first. Once I add 1, what happens is that after 2, we know that there's another number which is 3, right? So this becomes 793. Fairly simple, right? But if we add a bit too much, let's say for example we add 7 here. Once you add 7, what happens is that 7 plus 3, there is no larger number than that. Once you add 7 plus 3, you get 7, 8, 9, and then what happens after 9? So you have no other numbers which is larger than 9 to be represented to put on the rightmost space. So because you have no other numbers, you go back to the lowest number, which is 0, and the other number on the left will be added, right? Meaning to say that here we add 1 here. Again, once we add 1 here, I'll just put a smallish 1 here. I think this is a practice that you have been doing throughout your high school years. Plus 1, right? So you add 1 here. What happens at 9 plus 1? Again, we have no other numbers to represent that. How do we do this? You know, again, we just go to the lowest number, 0, right? And then it goes further left, right? And now 7 plus 1 is 8. Now this is added up. So basically this is what happens with any kinds of numerical system. You have a number, and as much as you can increase it, you increase it. 2 plus 1, you can increase it. You increase it to the next number in your numerical system. If you cannot increase it, you go to the left. If you cannot increase the number anymore, 9 plus 1 for example, you go to the left, right? And you add the number on the left, and etc. and so on and so forth. Now, with the binary system on the other hand, we only have 1 and 0. Now if you refer to your slides, there is this table which states that, for example, 0 for decimal, this is base 10, I'll just write 10 there, and base 2. 0 for decimal is 0 for base 2, right? 1 for base 10 is 1 for base 2. But once we get to 2, this is trickier, because binary only has 1 and 0, and this is already maximum. It's like this, it's already maximum. There is no larger number than 1. So what we can do is we can only add to the left, right? So it becomes 1, 0, right? And next we have 3. 0 is the minimum number in binary, so we can just add 1. It becomes 1, 1. Okay. Next we have 4, and so on and so forth, right? Once we have 4, what happens that this has maxed out. It's a maximum number. We cannot go larger than that because this is a binary system, right? So this is already maxed out as well. So what we can do is we just turn everything into the most minimum value, 0, 0, and 1 at the left post, and so on and so forth, right? For example, 5 would be 101, 6 would be 110, and etc. So on and so forth. Okay, so that is decimal to binary and vice versa. There is actually a way to convert these numbers from one system to another, right? And we'll have a look at the conversion of numbers now. Okay, the conversion of numbers involve you breaking the numbers down. Let's say, for example, you have 1101 base 2, and you want to convert it to decimal. So how do we do this? Basically, any numerical system goes like this. Let's say we have the number 83, right? We can actually break it down like this: 8 times 10 to the power of 1 plus 3 times 10 to the power of 0. Right? So this becomes 80 plus 3. This becomes 83. Brilliant, right? 83 is equal to 83.